Hi, Chong. Hi, Nancy. Do you actually understand what she's trying to express?
Sorry, I couldn't understand what you want to express.
Okay, maybe we ask you to write now.
Yeah.
So actually quite tricky, but I don't really like this kind of communication barrier.
Good afternoon, how are you?
I see.
Yeah, good.
Yeah, going great.
Hey, you know what? Actually, we can consider to do a device for Chunfeng, so that when Chunfeng performs some gesture, we can directly know what he wants to express.
That's a great idea. Since non-sign language speakers are not trained to use sign language every day, so it poses a serious communication barrier between normal people and the deaf. Other than that, it might pose the deaf to danger when they are expressing something to seek for help, but no one understands them. So probably we can apply some knowledge that we learned from microprocessor class.
Yes, exactly. What we did is only 3 major components, which is STM32 board, ADSL 337 accelerometer sensor, and also several jackpots. So this STM32 filter board will consist of CMSIS-DSP and CMSIS-NN, which can help to recognize the continuous gesture. So STM32 board will receive the analog signal from this sensor. This sensor will continuously send out the 3-axis time series flow data when user performs some gesture. Then the CMSIS-DSP will pre-process the signal and produce the features to be used as the input layer for the NN classifier.
Okay, so after that, those features will pass to CMSIS-NN to perform some recognition for the gesture detection. Finally, those gestures will output to the display in the form of word. Now everyone understands their expression now. That seems workable. So why not we start implementing it now?
Yeah.
So there's a website called Edge Impulse. It is a platform designed for software developer and engineer to build the machine learning application, and it is used in this project. Before using Edge Impulse, we must install Python 3, Node.js, as well as ST-Link driver to enable the Edge Impulse command line interface. The command line interface is used to collect data from device connected over serial connection and forward the data to Edge Impulse for data sampling through data forwarder. After the environment is configured successfully, we are ready to launch our Cube IDE for pin configuration. From the pin configuration, the PA0, PA1, and PA4 will be used as our ADC to receive raw X, raw Y, and raw Z data. PA2 and PA3 will be UART transmitter and receiver ports. LD2 will be using 2. So after generate the code, let's proceed to the main C++ code. On the main code in the while one loop, we will keep receive data from ADC 1, 2, 3 and save into variable raw X, raw Y, raw Z respectively. And this raw data will be sent through sprintf through the UART transmission to the Edge Impulse website. So let's proceed to compile the code as well as flashing the code. So after it shows download verified successfully, don't forget to press hard reset, and we proceed to the command line interface. From the command line interface, we input Edge Impulse data forwarder, enter. So it shows that device is now connected to project. So we are ready to launch the website and start the training process. Before that, we can verify the device. Yes, it is online. Then this will be our previous train data, and we have 37 minutes data and 7 label data. In order to train the new data, we can change the label as well as the sampling size. After finish configure the label and the sample length, we are ready to start sampling. So from the sample data, we can distribute it into training data and test data. So after satisfied with our dataset, we can proceed to create our 3 impulses, which is the spectral features, NN classifier, and abnormality detection.
Now I would like to explain the spectral features configurations for the accelerometer. So this features block need to be configured to extract the frequency and power characteristic of the accelerometer signals. So in this project, low pass filter with cutoff frequency of 3 Hz and 6 order of Butterworth filter is applied. So in this process, the raw signal is first skewed up to axis of 1 and then offset by its mean value. Then the Butterworth filter is then applied and root mean square of the filter output is added to the feature list. Then the spectral power configurations is set with fast Fourier transform of 64 and 3 peaks and 5 power edges. So at the end of this process, there will be 33 features generated in total for the input signal of 3-axis accelerometer. So the 33 features are generated from 1 value for the root mean square of the filter output, 6 value of the power peaks, which is frequency and height for each peak, and another 4 values for power buckets, which is from the 5 power edges minus 1. So together there will be 33 features generated.
After the spectral feature block, it will proceed to the NN classifier blocks. So the generated 32 features will be used as the input layer of the NN classifier. The number of epoch to train the neural network is set to be 150, which means that the learning algorithm will work throughout the entire datasets for 150 times. Then, the learning rate of how quickly the model is adapted to the problem is set to be 0.0001, while the confidence rate, which is the threshold score to trust the network, is set to be 80%. So the neural network consists of 4 layers. It will be consist of one input layer which will receive the 33 features. Next will be 2 hidden layers. First hidden layer will consist of 20 neurons, while the second hidden layer will consist of 10 neurons. After that, it will be the output layer which contains 7 features. 7 features will be the class of, which is the action that we want to recognize. From our project, this will be chest up front action, please, classroom, slow down, thank you, up front, up down, and yes. So from the model parts, we can know that our model able to achieve 89.2 accuracy and 1.29 losses, which is good enough. The confusion metric state that when we given the chest front back action, it will able to recognize at this accuracy.
Okay, then the last anomaly detections, which is a process to find the exceptions, outlier, peculiarities, and etc. are performed with a minimum score of 0.3. So which if the sample value above this score, then it will be tagged as anomaly.
Before exporting, we can do a live classification using our previous trained dataset or either live demo to verify whether we are satisfied with the trained model or not. If we are satisfied with the performance, we can proceed to the deployment. Then we can create a library in the form of CubeMX CMC spec by clicking the build. So it will generate the library CMC spec and they are ready to implement into our board.
Now, I'll be demonstrating our work to show that how the program is flashed into the Nucleo F446RE and demonstrate the hand movement recognition. After we've done our coding and building a neural network model, we simply launch the STM-Cube IDE, import the model files and other relevant files such as the main C++ file. Then, we click this little hammer to compile everything we have imported. When the compilation is completed, we then click this little button. This will flash the program into the board. After the board is flashed with the program, the reset button is pressed to make sure the program is properly programmed into the board. Then, the user push button is pressed to start our program. To connect the board to the HIN pulse, simply run this command in Command Prompt. Now the device is in standby mode. This is shown from the Command Prompt as well as the green LED that lighted up. By pressing the user button again, the green LED is off, indicates that the device is in detection mode, and we can begin our hand movement recognition. First, the movement is to be recognized chest, front, and back. Second, movement to be recognized as please. Third, movement to be recognized as slow down. Fourth, movement to be recognized as restroom. Fifth, movement to be recognized as thank you. Sixth, movement to be recognized as up and down. And finally, movement to be recognized as yes. The project demonstration is now complete. As you can see, there are some gestures will have difficulties to be recognized by the device. This is because the movements are similar. In future, we hope to enhance this device by collecting huge amount of data, so that the difficulties in recognition issue can be minimized. Thank you.